so many hands have been raised. Oh my goodness. Rishi, what do you think, man? Okay. So you said with each other. So how many things have to be there to interact with each other? So did you say inter or intra? Intermolecular forces means between each other. And so what did you say? How many had to be there? I put each. 2, thank you. Each other. So you need at least 2 molecules to interact. You cannot draw an intermolecular force unless you have 2 molecules interact. So intermolecular force is between molecules, right? Kim, what does intra mean then? Say it again. So if I'm an introvert, who do I like to work with? Myself, right? So if I'm an introvert, I don't necessarily like to work with other people, so it's more of a singular thing, like it's me and only me. So an intramolecular force means forces within the molecule or within the compound, right? So we actually already know every single intramolecular force. What are the 3 types of bonds we learned about? Ionic, covalent, and metallic. So write that down. The intramolecular forces are things that are happening within a compound, and those things happening within a compound are typical bonds that you already know. So if you guys want to move back up, because I know it's hard to see from back there. Okay, so the intramolecular forces are the bonds that we already know about, ionic, covalent, and metallic, right? Well then, on the second video, you were starting, and I'm sorry, this image really does just help you with that. The strong intramolecular force is the bond between C and H. What kind of bond is between C and H right here? Covalent, right? But between molecule A and molecule B, between them, we have a weak intermolecular force. Who got to the second video with the 3 intermolecular forces? Some of us did. Okay, what were the 3? Dispersion forces, dipole, and hydrogen bonding. Okay, so those 3 are really not truly bonds. They're just simply attractions. So the dashed line here represents attraction, where you have full-on, like, single bond there, which is a true bond. So attractions are intermolecular forces. They can be broken. They can be overcome, and that means that they can actually can allow for molecules to separate, versus a true bond, like an intramolecular force. It's really hard to break those individual bonds. And this second description here also helps you too. The inter is between hydrogen, chlorine, versus the intra, which is between the hydrogen and the chlorine that are attached. So I was hoping those pictures would help you out there. Okay, so the forces that you came up with were, and if you did not get down to the chart where you're filling those in, did I copy that here? Yes, I did. Okay. So here, let's go ahead and talk briefly about what you'll be putting in these boxes, because they're going to be influencing some of the questions you answer on your lab. So if you're in the back, go ahead and come back up to the front, please. It's hard to see back there. So I'm going to go ahead and write these up here. Oh, you know what, guys? I think my board is being funky. All right. So, London dispersion force. Yeah, okay. London dispersion force happens between what types of compounds? Nick. Nonpolar molecules. All right, so you are filling in your boxes as we go. Nonpolar molecules are what interact. And what causes, Jillian, these nonpolar molecules to interact? Because we all just watched the video on what polarity means, right? So we know that polarity means there's opposite ends of charge, whereas a nonpolar molecule does not have opposite ends of charges. So if you have 2 molecules that don't have opposite ends of charges, how do they interact? In flux, okay.
Essentially, one electron, or at any given time, one or like a couple electrons will have a charge, and because they'll have opposite charge, that's what holds non-polar compounds together somewhat.
Okay.
But it's not a strong enough charge to allow them to stick to a resolve of a substance.
Got you. So she's saying generally the electrons are evenly distributed like this, right? So I'm just going to put octet like that. 8 all across both. Meaning even distribution means it's a nonpolar molecule. Even distribution means it's a nonpolar molecule. For a nanosecond, for a split second, one of these electrons is like, ooh, let me get over here a little bit more. And so that's this side of the molecule becomes partially negative for just a hot second. Well, that causes this other molecule to go, whoa, electrons nearby. Let's scooch ours this way for just a hot second. And this side of the molecule B that I'm working with right now, becomes partially what? Positive, because it has a lack of electrons. So for just a split second, there's a partial negative and partial positive. And that's like a magnet, right? Magnets attract because of the polar ends, meaning a negative end and a positive end. And there's this just really faint attraction between these two molecules. That faint attraction happens just for a moment, and then it all goes back to what it started off as. That faint attraction is called London dispersion force. London dispersion force. And it's pretty weak. It's very weak because it just doesn't last very long. It's really minor of attraction. Well, this is the force that allows for a lot of, like carbon dioxide. Carbon dioxide is nonpolar, for example. It allows carbon dioxide to be attracted to another carbon dioxide molecule. This dashed line here is an attraction. And that's how we can make something called like dry ice, which is solid carbon dioxide. But it's so weak. The moment you put dry ice out in the world in normal conditions, what does it immediately do? It starts to actually sublime. It doesn't even hit liquid phase. It goes from solid and immediately goes whoop, out into gaseous state. So it immediately basically boils. It goes straight from solid to liquid gas, though, so it's called sublimation. So that's because that's so weak, it can't hold it together very well. Yeah?
What would you do to make carbon dioxide liquid?
Under extreme pressure, and allow it to slowly warm up. Under extreme pressure, though, because they can't go straight to gaseous phase, it has to go through liquid first. And we don't have that kind of pressure stuff here. Okay, so that's London dispersion for you. And we're going to do this more on Monday, but I want to make sure that you have a glimpse of this. Second force, somebody else. Chloe. Details. You guys can rewatch your video if you need to. I'm saying a lot of things, and hopefully you're writing some of that down. Details would be weak, allows for molecules to vaporize very easily, transient dipole moment, something like that. So some of the stuff Jillian was saying too. All right, so next type of force, guys. Dipole. So this is inherently telling you that if you see this pole part of the word, it's telling you it's the interaction between what kinds of molecules? Polar molecules. Okay, so polar molecules are key, and I'm just going to give a kind of cheesy drawing of this, but you guys have your ability to draw your own molecules too. Here's my two molecules, big blobs. What makes them polar? Okay, so the electronegativity differences, but in the end, what does that cause on this molecule? A partial charges, right? So partial positive and partial negative is just how I'm going to draw it. So if I've oriented this one in this manner, how would I orient this one? What would be on this side of the molecule? A partial positive because of the attraction component, right, between the negative and positive, and then this partial negative over here. So, again, we still just have a simple attraction, right? The attraction occurs where? Between the two molecules, right? So there's an attraction here. Is that truly a bond? No, it's not a covalent bond, it's not an ionic bond, it's not a metallic bond. It is an intermolecular force, which we call dipole, and I always abbreviate DD, okay? So, comparatively, these molecules up here, they experienced a pretty weak attraction because they just didn't have a really, they didn't have a true positive or true negative. There were slight positives and negatives that were so faint, barely there. But this one's got a more polar molecule, so it has a bigger, and I'll even draw the charges bigger for you, a bigger partial positive and negative, and a bigger partial positive and negative. So that little S thing is like just almost a figure 8. So their attraction is stronger. So it's going to take more energy to pull these two molecules apart, overcome their attraction. You look at carbon dioxide, and it's like vaporizing. This would be something like, let's see here, hydrogen chloride, HCl, like the images showed you in the simulation earlier. So these are pretty. They're stronger than London dispersion forces, but not as strong as the following group, which would be hydrogen bonding. Who's ever heard of hydrogen bonding? Where'd you hear it? Yes, in the video. Where'd you hear it before that? Anybody? Biology, right? What holds DNA together?
Hydrogen bonding.
Hydrogen bonding. Can DNA still separate? That's how it replicates, right? Unzip, throw in your nucleotides, and then retwist into your double helix. If you can't break your DNA, we would all cease to exist because we could never replicate our DNA, right? Our cells would just start to die and we'd never be able to reproduce them. Okay, so hydrogen bonding is what holds DNA together. So is it a true bond? No, it's just an attraction, right? The attraction is holding the double helix together. Still, it's an attraction, but the attraction is between molecule A and molecule B, but molecule A has to have what in it? A hydrogen with a partial positive, yes. Partial positive, but the thing it's attached to can be 3 different molecules or different atoms, and what are they?
Fluorine,
Fluorine, oxygen, or nitrogen. So it's one of these, and that's all. It's not all 3. It's one of these. Hydrogen attached to fluorine, to oxygen, or nitrogen. And I'm giving a really simplistic example. These could be definitely bigger molecules. 1 second, please. So I like to say hydrogen bonds are fun. Hydrogen bonds are fun. Fun. Got it? Okay. So remember that. You have to know that these guys, F, O, and N, where are they on the periodic table? So tell me about their electronegativity. They are pretty much the highest in the electronegativity area. So their partial negative is huge. They have a large partial negative, like almost a full negative charge, like an actual anion would have. So this significant difference in electronegativity differences makes this attraction super strong, but still not a bond, just a really strong attraction. So out of all of these, this is the strongest intermolecular force. So who's the weakest intermolecular force? Dispersion. Who's the medium? Dipole, and then strongest? Hydrogen bonding. And so hydrogen bonding, I wish I could change the name of that. We know it's not a bond, it's simply an attraction. Yes?
So is this present between molecular?
Oh, definitely. Can you see right here? What is this representing? A really, really polar, so I'm going to put very polar molecules. Very polar molecule. Okay, so it's more polar than the dipole. All right, so I'm going to pause for now. So what we're going to do is we're going to do our best to knock out visualizing some of the Vesper shapes through Vesper Yoga. And then we are going to go and build our structures that you have drawn. I will wrap up at the end of class with some more information, but I'll tell you that I'll show you what our structures look like before we move out. Don't be scared. No. I just have to show this to you. I have to show this to you right now. What? Linear is going to be so easy. All right, this is like my agenda for the world. The world to see. Wait for it. I know. Don't look at any of this. None of this is important. Wait, where did it go? There it is. Okay. Vesper Yoga. So we're gonna go in the hallway, and you have to listen. Okay. So let's do like 5-10 minutes. Let's get your big boy panties on. Let's go. Hallway. I'll tell you guys listen.
She tried to slip that in and she didn't just say that.
Wait. It's warm and quite nice tonight. That'll be nice. Well, I'm not. Okay, here's what we're gonna do. I'll call you back at the last 5 minutes of class or so to kind of wrap. But you guys know from yesterday how to build your structures, yes? Yeah. And I know I need to come around and I need to check every structure you've built. So basically, I think it's good if you build 3 to 4 structures in a small group at a time, so 2 or 3 people. The molecule kits are at the back, don't move yet. And you're going to raise your hand and be patient with me as I come around and help people with their fluid dot models, check out their structures, give them some approval of polar, non-polar, and so forth. You'll see on the big chart, where's that chart that you guys had for homework? You'll see on the chart, it's going to even ask you now about intramolecular forces on the very last column. So if you can figure it out, then go ahead and put that on there now, because we're going to finish it up on Monday. The intramolecular forces is what we just went over on next. So if you are ready, because your structures have been drawn, and you're pretty confident in what you're doing, go back and build. Otherwise, you're working on specs. 1, 2, and Chloe, you're working on specs. Okay. So please get in groups of 2 or 3. You have about a minute to decide what you're doing. You have a minute to get in a group.